Alright, lecture 4.4 corresponding to section 6.5 from the textbook. Guys, believe it or not, only 2 lectures left in college algebra. We are at the tail end of the course now, and these are the last type of equations we're going to study in the class. Those being exponential equations and logarithmic equations. Now the good news is there's no new material in this lecture. This is basically going to be us applying the tools we've acquired over the previous couple of lectures, the previous 2 to be specific. So in the previous 2 lectures we learned how to switch between logarithms and exponentials. We also learned some properties of logarithms. And that switching is going to be the name of the game here. So, loosely speaking, if you want to solve a logarithmic equation, change it to an exponential. If you want to solve an exponential equation, change it to a logarithm. So, switch it is the strategy. If we look at number 1, we have a logarithmic equation. We want to figure out under what conditions this is true. Well, take that logarithmic equation, switch it to an exponential. So, when you switch it, you get 3 to the 4th equals x, which is 81. So, 81 is the solution here. Here we have 2 to what power equals 7? Well, that's going to be log base 2 of 7 equals x. So, guys, I highly recommend you check out that book assignment from section 6.3. I recommended it 2 lectures ago. If you recall, 2 lectures ago, I highly recommended a book assignment. I think it was section 6.3, 7 through 35 odd. I said that book assignment will take about 15 minutes, and that it will. It only takes 15 minutes, and all it is practicing switching logarithms to exponentials and exponentials to logarithms. You need to be very, very comfortable with this. All right, get to a point to where it takes very little processing to switch between the 2. Because if you're fumbling and bumbling switching between logarithms and exponentials, you will not do well on the next test. You're going to be switching back and forth regularly. So please make sure you're very comfortable switching back and forth. Anyway, let's look at number 2. So if you recall, we said we had to isolate before switching. So let's get that logarithm by itself. An example. Oh, numbers are hard. This should be example number 3. There you go, fixed. Anyways, example number 3, we want to isolate the logarithm. So we have natural log of x plus 2 equals negative 5. We're ready to switch it, so that's e to the negative 5 equals x plus 2. If we want to get x by itself, we just subtract 2 from both sides. There's the exact solution. Notice the direction said be exact, so don't write that as a rounded decimal. Go ahead and leave it as an exact value. And then let's look at number 4. Let's go ahead and isolate that by subtracting 10 from both sides. We are now ready to switch that to a logarithm. Again, you want to make sure you're very comfortable switching from exponentials to logarithms. So it's going to be a base 2, input is negative 7, and we have x plus 3. Now, we have a problem here. Alert! We have a negative inside the logarithm, and we discussed that 2 lectures ago. This is undefined. 2 to what power gives you negative 7? No such number exists. So, if you ever see negative inside of a logarithm, there is no solution. Right? Throw it out. It's either extraneous or there is no solution. So, remember, you cannot have negatives inside of a logarithm, so please make sure you check. If we look at number 1, and if we plug 81 back in, we won't get negative inside of a logarithm. 2 and 3 don't have any negatives inside the logarithm. E to the negative 5 is going to be a positive number. And number 4, we get a value that is undefined. Alright, so let's look at the more advanced equations. So the idea with the advanced equations is we still have the same strategy. If we see an exponential, we want to change it to a logarithm. If we see a logarithm, we want to change it to an exponential. The difference is we might have to do some clever factoring, or we might have to apply those properties of logarithms. So let's look at this example. We have a problem in that we got an exponential in 2 terms that cannot be combined. But if you look at this structure in example 1 should look very familiar to it. What's that, you say? the voices in my head are saying that looks like a quadratic. And for once, the voices in my head are correct. This is quadratic in form. Notice we can factor with -7 and +2, right? Now it's not going to be x up front, it's going to be e to the x. And if we want, we can go ahead and check this real quick. Let's make sure our factoring actually works and that we're not going too insane here. Alright, so e to the x times e to the x is e to the 2x. Then you got +2 e to the x is -7 e to the x. All I'm doing here is foiling. And 7 times 2 is 14. So it works. So the check works. So we have e to the x -7 times the quantity e to the x plus 2 equals 0. The only way this could be true is if e to the x -7 is 0 or e to the x plus 2 equals 0. So this complicated equation is going to boil down to two simpler equations. Once it's in simpler equations, we just want to go ahead and switch it. So we isolate and switch. So for the first equation, we get natural log of 7. For the second equation, we isolate, switch it. We get natural log of -2. Remember, we cannot have negative inside of a logarithm. That solution does not work. It's undefined. So natural log of 7 is our winner. So that's an example of a more complicated exponential equation where we had to do a little bit of clever factoring before we can proceed. Now if we look at number 2, we see multiple logarithms. But the good news is they're both base 5. So we can apply properties of logarithms. If they're the same base, we can combine them together, at least via addition. So I'm going to go ahead and add log base 5 of x plus 2 to both sides. So I've got log base 5 of x plus 6 plus log base 5 of x plus 2 all equals 1. So remember, addition gives us a multiplicative property. So that'd be log base 5 of x plus 6 times x plus 2. Covered this in the last section. We can now go ahead and switch it. So switch that to an exponential. That's 5 raised to the first equals x plus 6 times x plus 2. So we're all the way back to the very first exam with solving by factoring. So go ahead and multiply that out. That's x squared plus 8x plus 12. Set it to 0. That's x squared plus 8x plus 7. So it factors to x plus 7, x plus 1. So x equals -7 or x equals -1. Now, just because a solution is negative doesn't necessarily mean it's extraneous. For example, if I plug in -1 into the original statement, so plug it in to the original statement, if I plug in -1, -1 plus 6 is positive, -1 plus 2 is positive. -1 works just fine. But if I plug in -7, we're going to get negatives inside of a logarithm, which is undefined values. So that one's actually extraneous. So the only solution that actually works here is -1. Alright, let's look at what I believe, or is in my opinion, the most complicated equation here. So the most complex equation is this exponential, at least in my humble opinion. Now, there's several ways you can tackle this. We can switch it to a base 5 logarithm. We can switch it to a base 3 logarithm. Or a lot of teachers, textbooks, and students, and generally speaking people, like to just natural log both sides. Not a bad idea. Natural log the left, natural log the right. I'm going to go ahead and change it to a base 5, just because that's what's on the left. So we have 5 raised to the x minus 2. 3 to the x plus 1. So you have to be very comfortable switching to logarithmic form. And then properties of exponents, so we can pull that power out front. Now we have to treat that x plus 1 as a singular quantity, so we have to keep it in parentheses. And then we're going to distribute. Log base 5 of 3 is just a number, so go ahead and distribute. So we got x times log base 5 of 3 plus 1 times log base 5 of 3 equals x minus 2. So what we're going to go ahead and do is get all x on one side. So I'll subtract x from both sides and get rid of any term that doesn't have an x. I'm going to get it on the right hand side. Remember what we do to one side, we have to do the other side. So all said, we get x times log base 5 of 3 minus x equals negative 2 minus log base 5 of 3. Now notice we got two terms we can't combine on the left-hand expression. We got an x with a rational coefficient and x with an irrational coefficient. Remember, if your variable of interest is in two terms that don't combine, factor it out. That's something we did frequently throughout the very first exam in the class. So here we'll have to do a little bit of clever factoring. And now we have it. We can now have our x completely isolated. Now, depending on what base of logarithm you use, your answer may look very different. For example, if you natural log both sides, it'll look quite different. But if you were to input both numbers into a calculator, you'd realize they're the same value, actually. And there's our solution. So this was, took a little bit of work. So just to summarize example 3, what did we do? We switch it to a logarithm. We, use properties of logarithms to pull that power out. We get all of our x on one side. We do some clever factoring, and then we are done. So let's go ahead and move on to example 4. And you may notice we have a base 3 logarithm and a base e logarithm. We cannot combine this because they are not the same base. Now your initial hunch might be, well, we'll use the change of base formula to make them the same base. And you can go this route, but it'll be very painful. If you look closely, you'll notice log base 3 of 9. Well, what is log base 3 of 9? Is it just a bunch of alphabet soup? Not quite. Log base 3 of 9. Well, that just equals 2. That just equals 2. Right? 3 to what power equals 9? That's just 2. Oh, and this problem just got a whole lot easier. By simplifying that logarithm, we have it. If there's no variable in there, it's just a constant. There's no variable in that log base 3. It's just a number. It's just some constant value. Treat it as such. So let's go ahead and isolate the logarithm that actually contains our unknown value. And we're ready to switch it. So e raised to the 3 equals x minus 1. Just add 1 to both sides. And there's our exact solution. So number 4 could be one of those problems that's absolute nightmare fuel if you try to change the base. Or you can do it in just a few seconds if you catch on to the fact that log base 3 of 9 can be simplified down to just 2. Alright, last example for the lecture. Now in this example, they are the same base and they both contain variables. So we do need to combine those. So remember, positive terms go to numerator, negative terms go to denominator. And we are ready to switch it. So that's 3 cubed equals x over x plus 1. So 3 cubed is 27. So we're back to test 1 now. Let's go ahead and clear the fractions by multiplying both sides by x plus 1. Distribute. Get all of our x's on one side. And divide accordingly. Now, if we go to plug this in, we cannot have negatives inside the logarithm. So this is an extraneous solution. So this equation doesn't actually have a solution. Alright, we are done-skis. So guys, just one more lecture left in the semester. So I'll go ahead and get that done, and keep up the hustle, guys. Have a wonderful day.